makeups work? If you even know. If anything, I'll email Mary or my
Um,
counselors.
yeah, so I totally forgot. I told myself I was going to record this one, but I'm going to record all the lectures, or at least try to record all the lectures.
Okay.
If you guys miss one for whatever reason, you have to either just like check in with me, or like try to set up a time with me to kind of just meet, and just so that we can kind of like rehash like what was discussed during that certain lecture, and you should be good.
Okay. But
Um,
that date is just a quiz. That's why I'm asking.
is it? Oh, duh, I wrote it
Yeah.
on the thing. Yeah, okay. Then yeah, I guess you have to set up a time to kind of make it up.
Okay.
Yeah,
Great. Thank you.
yeah. Speaking of homework, yeah, if you don't remember, we're gonna go like it's gonna go by recitation. So the recitation tomorrow's homework will be due Tuesday. Yeah, I think I got that right. Yeah, so that's how it's gonna go. It's just gonna go recitation, recitation. All right, and I don't know. I think it should be due at 11:59. I don't know. China might be like, oh, it's due at the start. So definitely ask her because it's it's her call. All right. Okay. So we did that. We're going out of order. Pre-test. You guys saw that the pre-test solutions are up. The average was a whopping 50%, which is okay. You know, like I said in the chat, like you guys were under very stressful situations. I just wanted to kind of see what it would look like if we did an assessment over like Zoom or conferencing, right? All that I ask, I'm just reminding you guys, I need you guys to have like show yourselves during a quiz or an exam. Okay, first quiz coming up. It's on the 9th. That's next week. So you need to be able to like we need to be able to see you like working. Okay, so please try and get that. And if you can't for whatever reason, just email me and let me know. Okay, and we'll work something out. Um, Canvas, any the grades. Yeah, so I'm still figuring out Canvas grades, the grade book. So um, I'm trying to like I still don't know how to like weight everything, but don't worry. Like I have all of your grades and stuff on a separate Excel sheet. I hand calculate it myself. All right. And China's like the kind of backup. She's like my second pair of eyes. All right. So if ever you really want to know your like current grade, you can ask us until I figure out the grade book on Canvas. If you want, you can calculate it yourself. I will still put up all the grades and assignments, but ignore what the output grade is for now. Does that make sense? So like if you want to know how you did on a homework, like we will put it up on Canvas, but the cumulative grade, it'll probably be wrong because it's not weighted properly yet. Okay. All right. That's Canvas. Homework 1 due tomorrow. We did that. I mentioned the quiz. Anything else before we get started? No? You guys good? You guys ready to rock and roll?
Yeah.
Yeah. Get ready to earn this bread. All right. We will we're moving into chapter 7. And chapter 7 talks about techniques of integration, and it kind of goes hand in hand with like chapter 6 because like 6 was supposed to be kind of like the applications, like it's supposed to show you like how integrals are used in real life. It's not all just areas and like volumes. It's also used for like probability functions and like other things, and like there's just a whole bunch of applications of integrals. Like areas and volumes are just an example. So in chapter 7 we are kind of posed with like problems that are more like complicated, that are like I'm not really sure how to integrate that. So there's like a theme um, of chapter 7. Also, I know my handwriting is disgusting. I apologize. I wasn't raised right. So if ever you need me to kind of like clarify anything, just like shout out or say something. Be like, what does that say? All right. I'll take a little offense, but it's okay. I'll get over it. So the theme of chapter 7, it's basically like how do I rewrite my integrand? Right? That's the whole point. That's why we're learning all these integration techniques. That's why, because we want to rewrite the integrand into something that we can integrate, if that makes sense, right? In Calc AB or in Calc 1, you learn basic integration rules. let's talk about them real quick. At this point, you guys can just kind of like unmute and like just shout out like basic integration rules, whatever you remember. Integration rules. Anyone want to kick us off?
Yeah,
I know. I don't.
Oh, maybe we should do a hand raising thing. Maybe that would be better. Sorry.
You know?
All right, just go ahead, Lamek. That's fine.
Okay. Basically, I don't know how to say it right, but like integral of the read times whatever equals. You can pull the 3 outside and everything. I don't know how to say the rule. Like, you understand what I'm saying?
I see what you're saying.
Yeah.
You're talking about
Multiplying and everything. Yeah.
constant, right?
Yeah.
Right. So like if I'm integrating like 5 dx, right? What would I get? Oh shoot. Right. This is the same thing as 5. Just 5x plus c, right? So basic integration rules allows us to pull out any constants from the integrand, right? Good.
Yeah.
Harry, I see that hand.
There's the difference rule.
Sum and difference rule. Okay, so so if you have like f of x plus g of x dx, right, in the integrand, that becomes integral of f of x dx plus the integral of g of x dx, right? Cool. Let's get into the more nitty gritty stuff, right? Like I'll give you guys an example, the power rule. Right, this one's a basic one that everyone should know, hopefully. This one says, I don't see any hands. Oh, I got a hand, Carlos.
Obviously, I think that one is like x to the n plus 1 over n plus 1 for the power rule.
Yeah. So if it only pertains to when you're raising some base of x to some power, you end up getting x to the n plus 1 over n plus 1 plus c. Oh my gosh, so many of you forgot your plus c's on that pretest. Carlos, you look really guilty right now. But yeah, there's a lot of you that forgot that plus c. It's a lot more important than you think. All right, I know your teachers probably like shouted at you to like kind of never forget the plus c, right? But it really does represent something huge. Another thing a lot of people forgot were the dx's. That's really important too. If you don't put that there, I don't know what you're integrating with respect to, right? So if you're not like being complete with your work, I mean, you're gonna pay for it. So moving on, after power rule, you guys learned another rule?
There's a f of b minus f of a.
F of b minus f. Well, that's the fundamental theorem of calculus. That's not, I guess it's integration related, sure, but I'm talking about, I don't know how else to say this, but the different types of integration that you guys
There's one for ln.
Like,
yeah, okay, all right, I'll take that one. Ln and e, right? You guys should know how to integrate this. I'm not gonna actually do this one because I'm just trying to save time here, right? You guys should know how to do ln of x and e. Was another like your basic trigs, right? All of them. Yes, even the inverse, even the reciprocal trig functions. All you have to know the derivatives and the integrals of them. Okay. Maybe not for this specific summer course, but in the come fall, if you're going into Calc 2, they expect you to know that stuff. All right.
Can you scroll up a little? I just forgot.
Oh, my bad. My fault.
Thank you.
You can also find these in oh shoot, not section 7.1. I'll get back to you on that one later. But yeah, so you guys have to know how to do these basic integration rules. I'm assuming you know how to do them. What else? So trig integral. So this is like sine of x, cosine of x, tangent of x, right? Then you have your reciprocals, cosecant, secant, and cotangent, and yes, you need. I'm talking about the integrals, not just the derivatives, right? Sine inverse of x. We'll get to. I don't know if I'll be able to show these, but we'll get to these later. All right, because you guys shouldn't know how to integrate these yet. I don't know. Do you guys know how to do this? Probably not, right?
I know.
You guys
My
know the
teacher taught it
derivatives.
to me. Yeah.
The derivatives.
Yeah,
My
the
teacher taught-
derivatives, but the integrals, you guys, I don't think you guys learned that in Calc
Yeah,
1.
my teacher taught all of that.
Okay. All right, cool. Yeah, we actually, hopefully, if we get to it, I can actually show you one of these today. So, I'll just start up for later.
I don't think we mentioned use substitution.
Oh yeah, how could I forget Yusub?
Yeah.
You know, I had a student named Yusub once. He was in my Calc class, and that was like the joke the whole year. Oh my gosh! All right, Yusub. I don't know if you guys learned it this way, but I don't know if you know, but Yusub is actually another word for it is a backwards chain rule.
Yeah.
All right, it's essentially you're like holding like a clump of things as one value, which is u, right? And then you're kind of like treating that as like the thing that was derived, if that makes sense, right? Because chain rule, it's like you derive the outer function and then you derive the inner function, multiply it with the derivative of the inside, right? But u sub, it's kind of like it's just the reverse of it. That's what that u is for, right? So hopefully you are all somewhat familiar with these. If you're not, I'll definitely, Khan Academy it or ask during the tutoring sessions or whatever. If you want to meet with me and go over anything, by all means, just set something up, But this kind of like brings me actually into section 7.1. Section 7.1 in the textbook, it's called integration by parts. Okay, and if you don't know, some of you do know. I actually saw one person do it on the pretest, so I was pretty impressed by that. But if you learned this, maybe you didn't know this. Integration by parts is actually backwards product rule, right? So there's a backwards chain rule. Well, there's also a backwards product rule. There is no backwards quotient rule. I think that would get a little too complicated. I don't know. Is there? I don't think so. There might be, and I just never learned it. But that'd be pretty interesting to see actually. But yeah. So here we go. We're moving on to chapter 7, and our theme, once again, our theme of this whole chapter is how can I rewrite my integrand into something integratable? Aha. Right? I should get that on like a fortune cookie or something. So I'm going to start this with a proof. And I know some of you kind of like tighten up when you hear that word. Some of you don't even know what a proof is. Some of you are just like, oh, I know what a proof is. That's the thing with the geometry and like the SAS and the SSS and the ASS or whatever, right? Like those aren't real proofs, okay? We're in college now, okay? You guys got to grow up a little bit. I'm gonna do like a really, really short and simple proof on why the formula of integration by parts is the way it is. All right, and once again, I'm gonna go at my normal speed, so by all means, just stop me if I'm going too fast. All right, you guys good? Yeah. All right, here we go. So, if we're doing the backwards product rule, well, then we got to use the product rule, right? Because that's I think that's a good place to start. So, if you guys don't remember the product rule, it looks like I derive two functions, and I'm going to call them u and v, are differentiable functions, right? Notice I'm like making like a statement in the beginning of my proof, and that statement will carry throughout, right? So I'm going to derive two functions. I'm going to call them u and v. All right, they're both of x. If you wanted to write them as this way, it's fine, but like it's shorter if I do it the other way. So this ends up being u times v prime plus v times u prime, right? Product rule. So it's the first times the derivative of the second plus second times the derivative of the first. Am I going too fast? Am I good?
No, you're
Okay.
fine.
Yeah. Great.
You're good. You're good.
Thank you. All right. So from here, we're actually going to do something. We're actually going to integrate, because we're talking about integration, right? So it makes sense that we're going to actually like kind of integrate both sides, and we're allowed to do this, right? I'm not breaking any math rules. I'm not going to math jail for this, right? So watch what happens when I integrate the left side. So let me just look at the left side. Well, you learned that the fundamental theorem of calculus, what the fundamental theorem of calculus told you was that like integrals and derivatives are actually like, they're kind of like inverse operators of each other, right? So what ends up happening is like this and this kind of cancel out, leaving you with uv on the left side. Does that make sense? Right, so that's just the left side. All right, on the right side, we're actually going to use one of the rules that, oh shoot, who said it? The sum and difference rule? Someone said it. But we're going to use the sum and difference rule to kind of break up the integrand here. Right, so we're gonna break this up into two pieces. So this then becomes integral of uv prime dx plus integral of vu prime dx. So far, so good? Okay.
Yeah.
Lastly, what we're going to do is actually subtract this guy over to the other side. Oh, whoops. And what are we left with here? A bunch of u's and v's and integral signs, right? I'll explain it in a second. Equal to uv minus integral of v. I'm going to rewrite this as du, all right? The reason why I'm allowed to do that is because these two pieces, the u prime and the dx, this is du dx, and the dx kind of just cancel out, you know? So it just leaves you with a du over here. Is that all right? So what did we just do? This is the end of the proof. Usually you write like you do something at the end. You like sometimes you'll see QED or like that box across. It just means that you're done with the proof. We're done with the proof. What did we just prove? Oh, Harry, what's up, man?
So the way that you canceled out the dx's on the left side,
yeah,
does that mean you could also turn the v prime on the right side into dv over dx as well?
Yes, you absolutely can, but for the sake of the equation, we're not.
Okay.
Okay.
Yep.
We're just choosing not to do it because it's still equivalent, if that makes sense. That's a good question. That's a good question. What did we just do? What did we just do? Well, we just said I can define two functions. I'm going to call that the blue function and the green function, right? Well, if I have a product, because remember, we're doing the reverse product rule, right? If I have a product of those two functions, I can rewrite it. I can rewrite this whole thing as this. And the reason why this is useful is because, once again, what's our theme? We are rewriting the integrand into something that we can integrate. So what does that mean? Does this always work? No, actually. This actually doesn't always work. It's just it's like a method of integration, right? That's why this chapter is called Method of Integration. All right? How are we doing? Is this like too out there? Are we good? Can I get like a
wait, 1 second.
thumbs up if you're good?
Can you scroll up a little bit?
Yeah, absolutely.
So wait, can you re-explain how you did that du dx thing and like how that canceled? Like, you know how you moved over that's from, you know, the red writing when you moved that from right to left? Can you just explain how you got that to be just du instead of dx?
Oh, okay, yeah. So
and why the u prime canceled out as well?
The u prime.
Yeah, like,
the u prime. Yeah. The u prime didn't cancel out. It's just notation. So you're talking about this piece right here, right?
Yeah.
What we have is vu prime dx. If I were to kind of like write this out, this is the same thing as v du dx. Right? U prime is the same thing as du dx.
Oh, yeah.
You see what I'm saying? And all that happened was just the dx is kind of, the terms actually do end up kind of canceling out with each other.
Yep, that makes sense. Yeah.
Okay.
I got it now. Yep.
Good. Once again, people, ask your questions. All right. Please ask your questions. If I'm going too fast, let me know. I do that sometimes, right? All right. What was I saying? I don't remember what I was saying. Oh, yes. Okay. So what are we doing here? We are integrating a product, right? A blue times a green, and we're splitting it up, rewriting it, so long as, maybe I can write this down, so long as I properly, that's not how you spell properly, John. Come on. Properly define four things: a u prime, v, and v prime. So long as I properly define those four things, I can use this equation. Yeah? So let's see this in action. I know you guys are done with the alphabet soup. But this is what a proof kind of looks like. This is called more of like an elegant proof, meaning like it works out so nicely and like you get to the answer pretty quickly. The more rigorous proofs out there are like, they take up like pages on pages on pages. But yeah, so here we go. Let's look at example 1. Integral of x times cos x dx. Now, if this is the first time you've seen integration by parts, right? At first glance, this is like, oh, okay, maybe I could just use like a u sub thing, right? Like where I kind of said u is like cosine or x. But when you think about it, you're like, there's an issue. The derivative of cosine is sine, and that doesn't appear anywhere in the integrand, right? And the derivative of x is 1, and that's not really going to help me. So I can't use u sub, right? I have to use a different method. Right? So here we go. Now you try integration by parts. What did I say? You need to define, you need to be able to define 4 pieces of this thing. 4 pieces. All right? A u prime, a v, and a v prime. All right, so let's see here. This means if I want to use this formula right here, I need to choose a u, and I'm just gonna write dv. I don't want to confuse you guys with notation. V prime. Okay, I need to choose a u and a v prime. That is a v prime. All right, so here we go. We're doing the reverse product rule. So here's one of the functions. It's just x, and the other function is a cosine, right? So I don't know. I didn't teach you guys the how to choose yet, but for funsies, I'm just gonna say u is equal to x, and v prime is cos x dx. Okay. You might see some other places that they might write it as dv is equal to just cosine x. It means the same exact thing. Okay. Does not matter. Like it means the same thing. All right. So we have our u, we have our v prime or dv, which means we can find a du, which is going to be 1 dx, and our v, which is, anyone know what the integral of cosine is? I know it's been a while.
Sine.
Wait, yes, yeah, it's sine. I almost forgot. Yes, it's sine, right? Because the derivative of sine is cosine, okay? So we have all the pieces that we need. We have all the pieces that we need to use our handy dandy formula that we just came up with, right? So why don't we try that? Let's rewrite this guy. This ends up being uv. So the formula goes uv minus integral of v du, right? So uv is, in this case, x times sine x minus the integral. Well, we found our v, right? We said it was sine of x, so why don't we write sine of x? And du, which is just our dx. So you guys can kind of see what happened here, right? We had something that we didn't know how to integrate, right? I didn't know how to integrate that as it was. So what did we have to do? We rewrote it. We rewrote it, and oh my gosh, that's not, I mean, that doesn't have any integration in it, and I know how to integrate sine, right? It follows that theme. We're gonna just rewrite everything, right? Shubham, what's up? See a hand?
His voice is cutting out. Like it's like really faint. I can hear it, but then it goes away.
Okay. Sorry, man. I don't think I can hear you. Do you maybe want to just type your question? All right, I'm just gonna type your question, and I'll look up in a second. I just want to finish this, okay? So where were we? So we broke it up, right? We rewrote the integrand into something we can integrate, and watch, we can get to a final answer. X sine x minus, well, what's the integral of sine x?
Cosine x, negative cosine x.
Yeah, negative cosine x, right? So this ends up being plus cosine x. And what do we never ever forget?
Plus
Plus
C.
C.
Constant plus C.
Plus C.
Plus C.
Yes, and we're done.
He's asking how we got sine x twice.
How did we get sin x twice? Because of the formula. How did we get sin x? Oh, that was Alvaro. Oh, thanks, Alvaro. Yeah, we just used the formula, right? We used this uv minus integral of v du, and we defined our uv and our dv and our du. Did that answer the question? Any other questions on this one?
Why don't we do the other side of the equation, the u integral uv prime dx?
Other side of the because that's the setup, right? So that's the original problem. This is the integral of, oh gosh, what is it? U v prime. U v prime. Yeah. You see what I'm saying?
Yeah.
This is what I meant when you had to choose a u and a v prime, because it was set up where we could choose one to be u and choose the other one to be v prime.
So this only works when there's like those two values, right? There can't be like it only. Okay.
It's a product rule. So it needs to just be a product of two functions. If you have three functions going on, that's going to create a poop storm. So
Yeah.
you won't be able to use that.
When would this not work?
When you get an integrand that, oh man, I don't know how to answer this. You get an integrand, I guess, when there's like not two functions.
That's like the only scenario. That's it.
Yeah, I mean, because like I said, right, that's how I introduced this. It's a reverse product rule.
Yeah.
So you have to have a product of two functions, otherwise it's not gonna.
But there are formulas for like more than two, right?
Yeah.
I think you can like just edit it.
Everything, man.
Yeah, I'm pretty sure like you can like edit it and like make it like really long.
Oh yeah, I'm sure. Yeah, I mean, like, believe it or not, you guys. I know you guys have like a lot of like math background. Usually, the kids in this class do. But believe it or not, I'm not trying to hurt your pride or anything. But there are integrals out there that you still don't know how to integrate, and that's why we need like computers and things like that for. Like the computers handle like the crazy integrals that you just can't do by hand. So, but yeah. What am I doing here? So we are moving on. No one asked it yet. Is no one gonna ask the question? No one's gonna ask the question. Huh? All right, I'll ask it for you guys.
Oh, Handel said he has a question.
What's up?
Handel? He said he has a question in the
Oh,
chat.
my phone handle. Go ahead.
I just saw.
Thank you. Oh, look at us being a good community to one another. Handle, go ahead, man. Hello? Handle?
He said, why do we find a v prime if we don't use it in the equation?
Why do we find a v prime if we don't use it in the equation? Oh, it's not that we find the v prime. We need the v prime
to find v.
Find the v.
Yeah.
Did I say that right? Yeah. I think.
Yeah.
Oh yeah. All right. Sorry, that's my first virtual O that I've heard. Like my students never like respond to me. So high schoolers suck. All right. So let's move on to the question that I want to pose to you guys right here, because no one's really asking it. Why didn't we choose the other way? Why? No one's curious. Like, what would have happened if I chose X to be?
Because you don't have to put the cosine X at the because like how over here it's the formula is integral v du. Mm-hmm. If you should choose the other way, the u would be cosine X, and it'll make your life harder.
But why? Why would it make my life harder? I want to live my life my own way, damn it. No?
Oh, wait, could there be an integral of 1? Wait, what makes yeah.
Like, don't try to do it all in your head, man. We're gonna do it. We're gonna make a blatant mistake. It's kind of like the milk is spoiled and you gotta smell it just because like you're just curious. You just want to know, right? Or like the plate is
I
hot.
can already tell it's gonna be like way harder just by like, because then you're gonna have to find like the integral of x and then okay, yeah, I can already see it's gonna get hard.
Okay, so some people can see it, some people may not. So let me do it until you all see it, yeah? So the other way. So that's if I chose u to be cosine x, which ends up, which would mean du is negative sine x, and then dv is x, and then v is x squared over 2. Was that too fast? You guys good? Right? If I write it all out, okay, uv minus integral of v du. By the way, there's a nice way to remember this. Okay, the way for some reason I remember, like it's the dumbest acronym ever, but like it's stuck with me since like high school. Ultraviolet minus the integral of voodoo. I don't know. It makes absolutely no sense, but it's stuck with me forever. This is actually how I memorized integration by parts. So, you know, you can use it if you want. Just make sure to
That's
you
cool.
know, give proper props to me when you use it, right? So
Yeah.
ultraviolet minus integral of voodoo. So I'm doing it the wrong way. Here we go. So UV, in this case, is going to be x squared over 2 cosine x minus integral of x squared over 2 du is sine x. What's wrong with this picture? I highlighted.
You have to do product rule again. And
Yeah, you would have to do integration by parts again on this piece, right? You would have to choose a u and a v again, and then if you chose wrong, you would have to do it again, and then again and again and again and again and again and again, and then you're like, F this, I'm like, done. Oh, I'm sorry, I wasn't supposed to say that. I'm done with this. I don't want to do this anymore, right? So what I'm trying to show you guys is, yes, there is a proper way to choose u. How to choose u, right? There's another acronym here. It's called LEPET, right? So this is a little nice little acronym here. It shows you how to choose your u, which means by default the other one has to be v prime, right? So if we follow this properly, we should always be able to do integration by parts. I'll put a disclaimer here just because like it's gonna keep me up at night if I don't tell you guys. This actually only works like 95% of the time. Yeah, it does. It's not foolproof. It works most of the time though. Okay, so yeah. So yes, each of these letters represents a type of function. So L stands for, you guys can probably guess, type of math function that starts with L.
natural logarithm.
Oh yeah, it's logs. So any sort of logs. As soon as you see a log, I choose u to be the u, right? So that's what L stands for. I stands for. Anyone want to guess? I.
Integral.
Integrals. What?
I don't know,
That ain't
like,
a
it's
type
just
of
Imaginary.
Oh yeah, imaginary numbers.
No, you guys are just saying random I words.
Instant, constant. I don't know.
Oh, no.
Interpret.
All right, I'll just give it to you. It's inverse.
Oh,
trig.
inverse function.
It's inverse trig, not inverse functions, inverse trig. I know, who would have guessed it, right? P stands for power, like x being raised to some power, right? E, you guys can guess E?
Exponential.
Exponential. Exponential. So that means like a to the x, like some number to the x power. Okay, and then the last one is trig. All right. So hopefully, I don't know, maybe I'm like kind of like reaching a little bit here, but hopefully you guys can see that the last two letters are E and T, exponential and trig. Does anyone want to take a guess? Like why do you think those two are at the end of the list?
Because when you find the for you.
Remember,
Because
okay, I'll give you guys a hint.
Most likely you're gonna have to redo it again because it's gonna be T cosine x.
Lamek, I have a feeling you learned this before and you're trying to.
No, I didn't learn it this way, but my teacher told me to just do the whole thing mentally and then everything. So yeah.
Okay. All right. Well, the hint
I learned it this way.
I'm going to give you is, what are we doing to u, the function u?
We go from u to du and we find the derivative.
Yeah. So what are we doing to u? We are deriving u, right? We are deriving u. Well, what happens when we derive exponential and trig functions? Okay, what happens when you derive e to the x?
Just e to the x, and
What
then
happens when you derive like sine?
You get, if you derive
Cos.
like cosine.
You get another trig.
Not the,
You get
yeah.
another
Yeah,
exponential
okay,
function.
yeah.
It never ever goes away, right? Power functions, they eventually do go away, right? If you derive it, if you try hard enough, right, it'll eventually go away. Inverse trig creates like a fraction. Logs creates a fraction, something that will like help cancel stuff out. Does that make sense?
Yeah.
I don't know. I'm just trying to
Yeah.
show you guys some insight as to like this wasn't just like random, you know. Someone actually thought this through, right? So I want to do another example, but I might have to push it to the video. Man. You know what? Let me just do this one. This is example 3 on page is it 418 in the PDF. It looks easy. It looks easy, but it's a little bit more complicated than you think, right? I know. Please, no one say 1 over x. You know, I will virtually slap you. Okay, if you do that, please. It's not 1 over x. The derivative of ln of x is 1 over x. But the integral is actually something you guys haven't learned yet. Most of you, right? Because a lot of you, those of you coming from AB, right? You guys haven't learned how to do this yet. Well, if you didn't know, you have to do this one by parts because I can't use u sub. I can't use the power rule. I can't use whatever, blah, 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 right? So this one is a parts problem. Now, the question is, what are my 2 parts? Because I only see one thing, right? I only see ln of x.
Yeah, wouldn't x be a part of the function log, natural log?
Yeah, so it's so like I only have like one function, right? Because I need 2 functions to do. Alvaro says make ln x u. All right, okay, I agree with that, right? Because that's the first letter, right? So that means I would make u is equal to ln x.
You can make b equals to 1.
Huh?
There's a 1, yeah, there's a 1 there.
Yeah, 1.
Yeah, so this is a very common trick. There's actually like, you know, there's an invisible 1 there. So we can actually make that 1 our dv function. Right, so here we go. Let me write it all out here. dv is 1 dx, and then du is 1 over x, v is x. So I don't know, I'm just gonna call in someone randomly. I hope they're here. Mariela, are you there? No? Mariela? Okay. Shahira? You there?
Yeah.
All right. What is try to do it off the top of your head. What was that thing, the formula for integration by parts?
Formula for integration by parts. It's
Can you do it without looking or no?
So it isn't it like
thing I said?
I'm trying to remember.
The sun's rays.
What
No.
is it?
It's okay. You can look at your notes. It's fine.
Okay, I'm gonna look at my notes. Let me see. 1. So it's uv minus integral of v du, right?
Yep. Ultraviolet minus the integral of voodoo. All right. So in this case, the setup goes x times ln x minus the integral of, watch what happens, right? Because we chose our u properly, this should work out nicely. This ends up being dx, just dx, right? Yeah, just dx. Look at that. And we know how to integrate that, right? I know how to integrate 1 is just x. And everything else just drops down. So look at that. You guys now know the integral of ln of x, all right? Ooh, I made a huge one. Sorry, I forgot about that. That's important. Look up a Khan Academy on it. I don't have time to explain that, but you need the absolute values in there. All right. I think that's enough of parts for today. I might put another parts example in Oh man, I might put another parts example or a parts thing in the video. All right, I kind of want to just like move on here. There's some things I gotta mention. So let's kind of cut it there for now. Section 7.2. Section 7.2. It talks about like trig integrals. And they go through something called reduction formulas. I'm just going to refer you guys to a chart. It's on page 428 in the it's on page 428 in the textbook. It has a bunch of, you know what? Why don't I just show you guys this?
I remember this.
428, 428. Right, yes. So it is, there's just a bunch of trig integrals from like sine squared and cosine squared, right? For those two, you have to use the half angle formulas. I don't know if you guys know what those are? Those are really, really important. Those are really, really important formulas because they pop up again in polar coordinates too. So if you don't know what half angle formulas are, look them up, all right? Write it down, like half angle formulas. Make sure you know what they are. But then on this page, they also go through like what happens when you raise sine to some value. What happens when you raise cosine to some value? It actually ends up reducing down into like using integration by parts. There's like a proof for all these, but you know you don't have to know them. You just have to know how to use these reduction formulas. Okay. In the fall, I'm not going to test you guys on it here. All right. So you guys can unclench and relax. Right. But in the fall, yes, your professors will go through this and they will tell you that you need to know how to use them. All right. Okay. I'm gonna pause real quick. How are you guys doing? I can't see like more than half of you, so you don't have to show me your face or anything. Can I just get some sort of like hand clapping or reaction, thumbs up or something? Tell me that you're still here and that you're kind of like alive. I know it's a lot of me talking, but it's kind of hard to do this without doing it. It's just part of Calc 2. I'm sorry. Okay, cool. So most of you. Thank you for that. All right, so here we go. We're gonna go back into our notes here. So that is 7.2. I'm just gonna skip right over it. It goes over how to integrate stuff like, you know, sine and cosine and, you know, cotangent and tangent. So if you want a refresher, definitely look in it to kind of like refresh yourselves, right? So so half angle formulas, reduction chart, and we finally arrive to section 7.3. Now I know I'm going to get cut off by time, but section 7.3 is actually something that isn't taught in Calc BC. It is a Calc 2, like college Calc 2 exclusive topic. All right. Some schools I've heard like some teachers teach this, but you know most don't. So I'll take this part nice and slow. Right. This part's called trig sub. All right. Section 7.2, we learned how to integrate trig. Well, section 7.3, we're going to apply some more trig to some integrals. All right. Trig sub can be boiled down to 3 scenarios. All right. 3 scenarios. The first scenario looks like this. The second scenario looks like, I don't know why I did that. The second scenario looks like this. And the third scenario looks like this. All right, I only have time to go through one of the scenarios. I will put the other 2 in the video. All right, but these 3, excuse me, these 3 scenarios, they actually come from the trig identities. I don't know if you guys can see it, right? If you guys can see the whole like tangent squared, oh my gosh, tangent squared theta plus 1, right? This one is 1 minus, oh shoot, I think it's a cosine squared theta, right? And so on and so forth. These kind of resemble our trig identities that we hopefully know, right? If you don't know what I'm talking about these. Like it's tangent squared theta plus 1 is equal to secant squared. And then the sine squared plus cosine squared, not plus 1, equals 1. Right? So with a little manipulation, you know, you can actually get to some like 3 forms, like these 3 forms. Okay, that's what I'm saying. And what we're gonna do is use trig to kind of like substitute in for like these x's, and it actually ends up working out. It's just some of these get a little crazy. All right, let me show you guys what I'm talking about here. What page am I on here for? Oh, here we go. So I'm gonna start off with a nice and easy one. Okay, everything is gonna be nice and sunshiny and make sense. Okay, so let's look at one example here. So 1 over integral of 1 minus squared dx. So at first glance, okay, at first glance, you're looking at this and you're like, maybe I can use a u sub. Oh wait, I can't use a u sub because the derivative of negative x squared is negative 2x, and there's no negative 2x, right? So I can't use u sub. And then you're like, okay, maybe I can use integration by parts. But oh wait, I only see one function there, and it looks pretty ugly. It doesn't really fall under LEPET, so I can't really use integration by parts. And then you notice, 1 minus x squared, and you're like, that fits one of the 3 scenarios, right? That fits one of the 3 scenarios, so I think this is a trig sub, all right? And once again, following the theme, we are going to rewrite this because I don't know how to integrate this as it is, yeah? So let's do it. So in this scenario, when you have square root of a squared minus x squared, sorry, I actually wrote that wrong. It's supposed to be sine squared. All right, when I have this scenario, a constant squared minus x squared, I'm going to use sine for x. Okay, I'm going to use sine for x. And hopefully you guys can just wait till the end, like to ask like why. It'll make sense in a second, right? So what I'm going to do is I'm going to say x is equal to sine of theta. Now, why am I using a different variable? Why am I not using x? Anyone want to chime in?
Because now you could do integration by part.
But we're not doing integration by parts.
1 minute.
Why can't I? Why can't I use like why couldn't I write it as like sine x here? Why couldn't I do that? Anyone want to guess?
Did you take the square root of both sides? Like you took this, it was x squared equals sine squared, you just took the square root, or no?
No, I don't think that would help.
Well, then you have x,
Oh,
and then
you
you have
could-
x on both sides, and you can't find the value of x like that.
Yeah, because then it'll be, if it was sine x, it'll be, and since x equals sine x, it'll be sine x, sine x, sine x, and it'll go like till infinity and beyond.
Okay, so the simple answer is, the simple answer is like it doesn't make sense because x is already taken, right? X is a variable that's already been defined within the function. It's what we're integrating with respect to. So we need to use a different variable. It's almost like u sub, right? Why do we use u? Well, you need to define something else. Does that make sense?
Yeah.
Okay. So yeah, we are going to define x to be sine theta. All right, and like see what we're going to do here, right? So watch. So if I have sine theta here, well, I can derive both sides, okay? Because I need to make a substitution, right? So I need to substitute. So I'm going to derive both sides with respect to theta in this equation, right? So I'm going to do d theta here. Right, so this ends up being, I'm just gonna shorthand this, x prime, actually, no, I'm sorry, I needed that. So this ends up being dx over d theta is equal to, well, what's the derivative of sine theta in terms of theta?
Cosine theta?
Yeah, it's just cosine theta, thank you, whoever that was, Handel. Cosine theta, right? So I have this here. I can multiply both sides by d theta. And watch what happens. I get dx equals cos theta d theta. Now this should look kind of familiar, right? Because this is actually the same step that you have to do with u sub, right? You define a u, you derive it in terms of u, and then like you have to make a substitution. Well, we're going to do the same exact thing here, right? I'm going to replace this dx for a cosine theta d theta. What else am I going to substitute in?
The x for sine theta.
Yeah, thank God you guys are listening. Yes, I'm gonna substitute in sine theta for x. That's the whole point of this, right? I could not integrate that. I did not know how to integrate that as it was. So I'm gonna rewrite it as something else. So this ends up becoming 1 minus, not x squared, but sine squared theta. And I also need, remember I said that dx is important? I also need that new dx, which ends up being cos theta d theta. I have everything I need now to try to integrate this with respect to theta now. So what do I get here? Well, let me kind of rewrite this a little bit here. This ends up being cos theta over square root of 1 minus sine squared theta d theta. And what I was saying in the beginning of this, it uses, this is why trig is so important. It uses those two definitions, right? Because watch, if I have 1 minus sine squared theta, well, isn't that equivalent to something?
Cosine squared theta.
Yeah, using the definition above, right? If I were to just swing this over to the other side, I end up getting cosine squared theta. And you're like, oh, snap, I think I see the puzzle pieces coming together. If this whole thing under the square root ends up being just this, well, what's going to happen to that square root?
It's going to square root, so it's going to be cosine theta, so it's going to be cosine theta over cosine theta.
Yes, and something beautiful and magical happens here, right? Oh my God, I'm sweating here. Something beautiful happens here, right? The cosine and on top that came from the substitution, once again, this cosine came from the substitution, and then the cosine squared that reduced down to a cosine on the bottom end up canceling out with each other. Whoops, for my theta, right? So what are you left with? Integral of 1 d theta. Wow. Oh, man, it's beautiful, isn't it? Man, don't you just, oh.
Wait, can you scroll up a little bit?
Oh, my fault.
Give me 1 second.
Sorry. Am I going too fast? Sometimes I just get too into it, you know, and like, I just get in the zone and then just.
No, it's okay. I was just missing just like one part.
What were the two trig identities as well?
The two trig identities, yeah. So tangent squared theta plus
What
1.
about for the third one? Is there anything for the third one?
There is. It's, I think this one is secant squared theta minus 1.
If you just know the third one, you could figure out the other two.
Yeah, just refer to the video later on. And
okay.
Yeah, because I'm going to show you the two other examples in the video. Oh my gosh, it's 210.
Wait,
oh my gosh, it's 212. Holy crap.
Wait, can you scroll that down so I can get the rest? Yeah, that's fine.
Hey, John, real quick. So we use the trig sub when we can't use integration by parts or the u sub.
Exactly. Yes. So all these methods of who asked that? I can't see who's. Is Hendo?
Yeah.
Okay. Word. So yeah, I'm showing you like this plethora of methods to integrate, so that like you think of them as like tools, right? Like sometimes you might need a screwdriver, sometimes you might need a hammer, sometimes you might need something else, right? I'm trying to give you all these tools so that you can integrate most integrals, right? Yeah. We're not done yet because there's a really important part. If I integrate this, you guys got this down? You guys good?
Mm-hmm.
Oh, by the way, this is recording. I forgot to mention that. This is recording. I'll put up the link to the recording after the lecture, right? So I integrate this, I get theta plus c, right? Because I integrated with respect to theta, so I get theta plus c, right? So I cannot leave my final answer like this. Why?
Because you plug something in. So you
The
have to
original
like
variable was I.
yeah.
So then it'll be
You change the
arcsine
Someone
x.
said it. I think Alvaro said
Arcsine
it.
x. So
You change the variables around, so you have to plug everything back in.
I did something rude, right? If you left your answer like this, that's like the equivalent of like putting your cup on a table without a coaster. It's rude, right? I gave you a problem in terms of x. You better give me an answer in terms of x. Make sense?
So would the answer be arcsine x?
Right, but how'd you get that?
Because I went back to the x equals sine theta, and then I basically solved for theta.
Good, right? So we can't leave it in terms of theta, so we have to go back, all the way back to our original substitution. Remember, we said in the beginning, x is sine theta. Well, if that's the case, sorry for all the arrows, if that's the case, if x is equal to sine theta, I can arc sine both sides and get sine inverse of x equals theta. And now I make the substitution and get my final answer, which is sine inverse of x plus c. Why did no one in the beginning notice that? This is the derivative of sine inverse, no? No, you guys don't see it? No? Well, maybe you guys don't know. Yeah, we just proved like why the derivative of sine inverse is the I came back, right? I know, he's so cool. So yeah, all right. I know I kind of like flew through that. I apologize if that was like really fast, but I wanted to get at least one example of these in. I apologize for running over time. I know it's very precious to you all. Be on the lookout for a couple of things. This recording, okay, of this lecture. Another video I'm going to put up, okay, of the different trig sub stuff. I'll tell China to go over some other trig stuff during recitation, and then your homework that's due tomorrow. All right. Hopefully this wasn't too bad. That was like about the speed we're gonna go, and especially with series, I might even have to go a little faster. So once again, I've had some people reach out to me already, you know, about like the option of like, you know, possibly going down to Calc 1. I'm going to reiterate what I said during the first class. It's not a bad option. If you drop down to Calc 1, because then you're kind of rebuilding your Calc 1 foundational stuff. Because once again, in Calc 2, they're going to expect you to know your integration stuff, your trig stuff, everything like that, like the top of your head kind of thing. All right. So if you're contemplating it, by all means, you know, I won't take any offense to it. If you want to talk to me about it, by all means, my e-door is always open. Okay. If there are no questions, you guys are good. Lecture 2 down. We got like 10 more to go. So excited.
Have a great day.
All right. Take care, guys.
Thank you, John. Have a good one.
All right.
Okay.
Thanks, John. Have a nice day.
Thank you.
Bye-bye.
Thank you.
John, I have a question. You said something about half. You said something like half circles. What was that?
Half circles. What part of the lecture?
It was like after how do you choose C or U?
Half circles.
It wasn't like directly half. It was like something around like half something. I just don't remember.
Oh, half angle formulas. Yes.
Half angle.
Half angle formulas. I'll give you one of them. All right. One of the half angle formulas. If you see it, you might recognize it. It's if you have cosine squared theta, it's like 1/2 theta. Oh my gosh, I'm butchering this right now. I think it's plus sine. No. Hold on, brain fart. Oh, here we go. Okay, cosine squared theta is equal to 1/2, 1 plus, sorry, it's 1 plus cosine of 2x. There you go. There it is. So that's one of them. There's one for sine squared, right? So the point of these is just to reduce the exponent, because like if I tack on an integral, like I don't know how to integrate that stuff as it is. So I have to rewrite it and then integrate it. I was supposed to use thetas. These are thetas. These are thetas.
Oh, okay.
Okay.
Thank you.
Anytime, man.
Everyone.
You too, buddy.